Okay, yesterday we had a look at this problem here for the shear stress distribution or the distribution of shear stresses in the solid rectangular section. Just note that this is, when we say the shear stress distribution, we're referring to both the vertical as well as the horizontal. And we actually said that the vertical and the horizontal shear stress distributions are the same. If we just flick forward in the course book to this page here, which would be page 314, you can see that it's actually for a channel section, but I might as well introduce it here. So you could make a fold along here, and you could make another fold along here. So once you make the fold, of course, you can see the cross section is that of a channel section. But for this purpose, let's just have a look at the vertical shear in the web. So that's like holding this end here as if it's fixed in, as shown here. So holding one end and assume that it's under a bending moment diagram, or because there's a vertical load being applied right at the end of the section. So pretend there's a vertical load being applied downwards at the end of the section. And the bending moment diagram, of course, is going to be linear. I'm going from 0 right at that point there to a maximum there. So I could, I suppose I could just show the load that's been applied, and I could also show the bending moment diagram, and I could also show the shear force diagram right there. So we are not concerned with the bending moment diagram, but of course we note that without the change of bending, there wouldn't be any shear force anyway. So forget about the flanges, just worry about the web down here. And so here you can see the vertical shear. So I've drawn squares at each point here. So this square here would represent the shear at that point right at the center, and then that would be the shear at that point right at the center. And we can see that the complementary shear stresses that we talked about last time, so these would be the vertical. On the other side, of course, it's going upwards for equilibrium. But what I'm drawing attention to are these ones here. So that would be the horizontal, these would be the horizontal shear stresses, which would be in equilibrium with the vertical ones. So if that helps you understand what it means when you put the load going downwards or upwards, doesn't really matter which direction. You would of course get the vertical shear, the vertical shear stresses, and these would have to be balanced by the complementary shear stresses. And of course, blobs on the either side of each other, that shear stress is equal, and it's in the opposite direction to the one on the next side. So they would cancel each other out. Okay, so that shows the horizontal one, and the horizontal one, of course, acts in the longitudinal direction, which is along the length of the beam. So we'll talk about that later on, but I thought it might be nice just to show that, or just to introduce you to that at this stage here. So I remember the question was find the distribution of shear stresses in a solid rectangular section. So we could draw the solid rectangular section like here, and we could label it up. The B is the breadth, of course, and then D is the depth of the section, which we will see there. So B is the breadth and D is the depth. And first thing to do is to identify the neutral axis of the section, which we would show there with the neutral axis. and you might want to introduce your conventions. So we'll call y in that direction there, and I think so I could either call this one x or z. I think I'll just call it z. No, hang on, I'll call it x. I'll call this one x, and then z would be in the plane. Okay, so we'll call that one x, not that it matters. So if the rectangular section was under a bending moment m, and we say let's want to calculate the stress at that point there, we would use sigma, which would be the stress acting in the page, equals the bending moment from the bending moment diagram times y, which would be the height at that point there. So that would be y, which is the axis. So y at that point, sigma equals my over I. So remember that at that point you would also have vertical shear and you would also have the horizontal shear, and the equation for both the vertical and the horizontal shear, because they're the same, is similar. So the shear would be equal to the shear force multiplied by a dash y. No, sorry, I think we're calling it in these notes here, I think we're calling it s dash y. And then it would be divided by I multiplied by b as a function of y, or the breadth as a function of y. So if we had a cross-section like, for example, if the cross-section had been something like that, and then that was the neutral axis, and then that was the y. So if the cross-section had looked something like that, then we can see that b, the breadth, is a function of y. So when y is here, then it takes that value there, and when y is 0, it takes that value, and when y is at the top, it would take that value. But for a rectangular section, it's obviously constant, so it's not a function of y. So for the case of a rectangular section, I'll just call it IB. So let's try and decipher this. So the shear force is from the shear force diagram, like the BM is from the bending moment diagram, and this is the first moment of area at that height y. So what it means is, I'll draw that out again, okay, and then this time here I'll draw at that height across there. So I'm not going to be drawing the whole section, I'm just going to be drawing that bit there. So the rest of the section you could pretend was in dashed lines. And what we want to do is, we've made our slice here because it's at that height where, or it's at that distance y from the neutral axis, where we want to work out the shear stress. Incidentally, the shear stress would be the same whether it's here or here or here or here. So anywhere along this line within the section, the shear stress tau would be the same. Perhaps I should have said tau is a function of y as well, and sigma is also a function of y. Okay. So what we'll do here is that s dash y is the first moment of area, and it's the first moment of this area. Okay, so it's the first moment of that area, and it's the first moment of area around the neutral axis. So that's still the neutral axis. Okay, so you could call that NA again to call it the neutral axis. So what it means is that this whole area is going to be called, so the area, the shaded area is going to be A dash Y. Okay. So the shaded area is A dash Y, and the first moment of area of A dash Y about the neutral axis is going to be, and I'll put a cross there, it's going to be that height there. Okay. So that's the centroid of A dash Y, and it's going to be that distance down there. So that distance is clearly Y plus d over 2 minus Y, because that one, d over 2 minus Y would be that distance divided by 2. Okay, so that would be your that would become your A dash Y, the area multiplied by, and I think it called it Y bar. Let me just have a look at the notes if you don't mind, just so that we're not so that I'm not changing notation, because I know that can be a bit confusing. So yeah, so A dash times Y bar. So this distance here is your Y bar, and the A dash, which is the shaded area, multiplied by that Y bar, is going to be equal to your S dash Y. Okay, so that guy there is this term here. So we can see that hopefully that this equation is quite similar to that equation, sigma equals my over I, where m is the bending moment, except that in this case here it's the shear force multiplied by S dash Y over IB, and I've just explained how to calculate S dash Y, which is the area multiplied by that distance there. So you could probably see to yourself that if Y was d over 2, which is up there, there's no area to slice off, or if it was just a hair breadth below, so the whole of that term would be 0. So that sort of tells you that the shear stress distribution up here is going to be 0. And if you're also wondering why it's 0, you could think of the longitudinal shear stresses or the horizontal shear stress. We said that the vertical and the horizontal are the same, and up at the top surface there's the atmosphere, so from that reasoning it has to be 0, and you could make the same reasoning down there, and it is going to be maximum down here. So if y had been 0, then we're talking about d over 2 multiplied by b times d over 2 divided by 2, and that would be the maximum value. So the shear stress distribution would look like that, and that's both the vertical as well as the horizontal, or longitudinal. So I could put that as a plot of tau, and that is going to be your x-axis. So that's a cross section. So that's the x-axis there. Sorry, got that wrong, haven't I? That one would be y. Yeah, that one is obviously y, and then this axis here would become your tau. Okay, so the tau, the shear stress, whether it's vertical, horizontal, it's the same at any line across here. It would be the same. A logical question might be, okay, you're taking the slice here and taking that area there. What happens if you use the other area? And if you use the other area, you'll get exactly the same answer. So I'll rub this out a bit here. So I hope that's all right. And So back to square one again. I'll put that in dotted lines there. So we make our cut here, which I'll draw solid. Okay. And last time, so we wanted another shear stress at that point, or that point, or that point, so we do a horizontal cut. And last time I took that area there. What happens if I took this area here? So if you took this area here, it's all fine, and it would still work out, but you've got to bear in mind that a bit of this, half of this is below the axis and the other half is above, so you would probably have to split that up into, let's just call it area 1 and then area 2, and then area 1 would be that one there multiplied by that distance from here to the center, and then it would be negative, or because A1 and A2 would be on the other side, you would have covered that with Lucas and Quincy. So they're not additive, they would be subtractive. So one of these would be negative and the other would be positive. So the area 2 would be there, and then centroid there, and then that distance there. Then again, you're working out your S dash, and it would work out to give this exactly the same numerical value had you done it, had we done it that way. Okay. So obviously this way is easier because you're not, because all of the shaded area is above or below the neutral axis. All right, so I'll just mention that as one of the subtleties of the equation. Okay. So so that should be, you know, this equation is not really that hard to operate, as we can see from this example in this chat about it. Now, if you go to the Dropbox, for example 1, so let's go to the Dropbox here, and then I've got the type John Butterworth solution, which you can see there, that I talked about, and then I've got my YouTube solution, or my LiveScribe solution, so you can just go to that link there, which should be the same, and you'll listen to me chat about this for a while. And then there's some Piazza questions that will just explain what we've just described. Okay. And then finally, I think I found a YouTube video by a guy called Jeff Hansen last year, which I thought explained it quite well. So that's all there if you want it. So let's move on to example number 2. So I'll take this one out for now. So we've got a timber beam, and it's made from 2 bits, 200 times 50. So that dimension is 200, and that's 50. And that's 200, and that's 50, and then the 2 bits are glued together. Find the distribution of shear stress in a cross section where the shear force is 100 kilonewtons. So that could be, for example, a cantilever with 100 kilonewtons. So that would have a shear force diagram like that of 10 kilonewtons. So it could be like that, or it could be a beam like there, maybe 2-point loads. That would be 10 kilonewtons, and then that would be 10 kilonewtons, and then the shear force diagram of that would be like that, and the shear force diagram of that would be like that. Okay. And that would be your 10 kilonewtons. So I'm just trying to emphasize again that this is from the shear force diagram. Because if we had a beam like there and that was 20 kilonewtons, then it's 10 upwards and then 10 upwards on that side there. So that would be down like there, but that would be your 10 kilonewtons for the shear and 10 kilonewtons for the shear there. So it's saying that the V is the shear force from the shear force diagram, not necessarily the load that's been applied to the beam. And all of these examples, the shear force is 10. So now you've got your 2 bits of timber, and the 2 bits of timber have been glued together. So there's a glue that's been acting. We'll show the glue. We'll show the glue along that surface there. So if we how do we know the shear strength of the glue? So just for example, if we know that that distance there is 50, millimeters. So if, for example, we had taken that as 50 millimeters, and then if, for example, we said that the overlap here was 50 millimeters, so we've then got a bit of glue, and that bit of glue would be 50 by 50, so not drawn that particularly well, 50 by 50, so that just represents that bit of glue joining the 2 surfaces together. So you could pull it apart until the glue itself fractures, work out work out what load it was when the glue fractured from your experimental test, and then divide that by this cross-sectional area, 50 by 50, and then you would get the glue strength, which is normally specified as a shear stress. So how do we find the distribution of shear stress in a cross section where the shear force is equal to 10 kilonewtons? So we're assuming that the glue we're assuming that the glue is strong enough across there. So I'll just talk you through how we might do the solution. First of all, you've got this top surface, you've got that bit there. So we're going to have to be calculating the second moment of inertia. So we could work out the second moment of inertia of this bit, taking it out by itself. And we know that's going to be 1/12 BD cubed, so 1/12 times 20 times d cubed, and that is the second moment of inertia of this section here. Now we now need to, so I'll just draw that down there, okay. And then we've got this second bit here, and the second moment of inertia of this one here about its own neutral axis. So if that was 200 millimeters, then we're saying at 100 millimeters, which would be halfway up, that would be its neutral axis. And the second moment of the second moment of area, or the moment of inertia of this one here, would be 1/12 times the breadth times 200 cubed. So here is where we would remember the parallel axis theorem. So the parallel axis theorem would tell you how you can shift the neutral axis. So this would be I self, or the second moment, or the neutral axis of the top bit. And we then need to add on that distance here, okay, and which would be the area. The area would be the area of 200 times 50, which would be that area multiplied by that distance. So that distance would be the position of the neutral axis of the top bit to this one here, which would be the neutral axis of the compound section. Okay, and we'll do exactly the same here. We'll work out the second moment of inertia of this bit here, and then we'll add that onto this area times that distance, which would be the shift, squared. So when we've got the equation, so tau as a function of y is equal to V, which is the shear force from the shear force diagram. So shear force diagram multiplied by S dash y, and then divide that by IB, where B is a function of y. Now you can see that there's going to be some glue there. So, and I think you can clearly see that the glue has some width. So the glue isn't over the entire bit here, which you can see. So the glue is just confined to that bit there. But nevertheless, there is going to be a jump from just under the glue to just above the glue. So a hair breadth under the glue to a hair breadth above the glue. There is going to be a jump because this B changes from 50 below the glue. Suddenly it changes to 200 above the glue. So there is going to be a jump. So that should, anyway, you should have enough information now to be able to work out, to be able to solve that, and to be able to draw the distribution of the force in the glue. What I would say at this stage is that you're going to have to work out the neutral axis of you're going to have to work out the position of the neutral axis, so that we can get the shift, the 2 shifts squared using the parallel axis theorem. So to work out the position of the neutral axis of the combined section, I suppose you could take that as a datum point, and you could multiply that area by that distance there, and then add that multiplied by that distance there, and then divide it by the whole area. A faster way to do it, and that would give you the position of the same neutral axis, which would give you that distance there. You could choose, for example, to take that axis as your datum point, and then you are then only concerned about that area multiplied by the centroid of this area, which would be here. So you would then multiply the area by that and divide that by the area multiplied by that distance, and then you can have enough information to solve that distance. So I think there's enough information for you to be able to work out the second moment of inertia of the combined section. And then, of course, the S-Y. What do we do about that? Now, the distribution of the shear stress. So I'll get rid of that. The distribution of the shear stress of the section along there. So, sorry. So the axis, just to reinforce, the axis, that axis is the 0 of the y-axis, does go through the neutral axis of the compound section. So you could say, based on what we described for this one here, where we said that the shear stress is going to be greatest at the neutral axis where the y is 0, that's still going to hold. So you could calculate the shear stress at that point. So maybe we might get a value. Maybe we might get a value there. So I'll just get rid of NA since I've already described what NA is, and then I'll just put that as the shear that we're calculating. So the shear is going to be maximum at that value. The shear is going to be minimum at that value there. And as we've talked, you would expect there to be a jump or a step change below the glue and after the glue. So saying that one there is 0, you might say a hair's breadth above, it would be like that. So that's a hair's breadth above for the stress, and then there would be a jump, and then a hair's breadth below the glue. Sorry. So take that down there. A hair's breadth down the glue, it would be like that, and then that would go down to 0 as in a parabolic shape. So when it says find the distribution of shear stress in a cross section, that's what I would expect it to be. Maybe even a bit more drastic than what I've shown in terms of there. So above, it could be here, and then below, the shear stress would be much higher. And if you wanted to, you could put a horizontal line there. Okay. Right, so that would be the distribution. If you wanted to work it out at the neutral axis, then what we would do is we would cover that bit there, and we would take that, just that portion there. So that's quite handy, so let's just get rid of that. So we would find the new, so we would just concentrate on this section here, work out its dimensions, work out halfway down so that we can work out the S-Y, and we would then work out the area of that section there, and then that would give you that value of shear stress at that position. Okay. So yep, so you can work out that value, you can work out that value, and you can work out that values. Okay. So that would be how to approach this problem. So if you looked here on the Dropbox, you can see that's pretty much what we've just described, and the calculation to work out, and the calculation to work out the distribution of the shear, and also the required glue strength in terms of tau that would need to be there under that shear force in order to stop, in order to keep the section together. So if that shear stress is exceeded of the glue, then the section would separate, or there would be fracture of the glue, and then the two bits of wood would be working separately. So we've sort of talked about that before, right at the start, when we were talking about fracture of glue along those bits at the ends. Okay. So there's a written, so for some of you there's a written solution there that you might like. I've also got a longer solution. So if we go back here and we look here, I've got my LiveScribe solution, and then I go through that solution and all of the steps in order to work out all of the values that you can see here, and then finally work out the strength of the glue, which would be needed. Okay. So everything that you need would be here. So this, as we've described, the shape, calculation of the shear stress at the neutral axis, which we can see there. Sorry about that. So the first step would be to work out your area 1 and your area 2, work out the second moment of inertias, and then find the position of the neutral axis, as we just described. And then once we got the neutral axis, then we can work out the I of the combined section, assuming of course that the glue is strong enough to stop the two sections from separating, which we assume that it is. And so I've got a value of I. Over here, that's the shear stress distribution that we've talked about, and I mentioned that the air there ensures that the shear stress at the top and bottom are 0. Calculation of the shear stress at the neutral axis, you can see how I've done it here. So that would lead to that value of 1.163, which you can see there. Then on this page here, you can see that step that we talked about, above or below, and we're able to work out the two values there of the stress, which we can see here. And then conclude that by calculating the shear stress at some other points, and then saying what the strength of the glue would need to be. So the strength of the glue would need to be at least that value there. So there's a LiveScribe solution that would go through the details of those if you needed to go through them. Okay, so let's move on. So shear stress at a free surface. Consider a small cube of material with one face lying on the surface of the beam. It's free, there are no surface tractions applied to it, and we conclude that the shear stress perpendicular to any free surface must be 0. So we've already sort of set that because we set the shear stress along here and along here must be 0. And we've already said that the shear stress on there and on there is also 0. So that's no more than what we've talked about before. Now this thing about shear flow, referring again to figure 8, the shear stress on the upper surface is shown to generate dq. If we now calculate the intensity of this force per unit length of the beam, we obtain the so-called shear flow, which is down there as equation 13. So now let's have a look at example 13, which we'll see here. So this is the same beam that we had before, but before there was glue along that surface there. So glue isn't, I don't think glue is particularly sustainable. There's some environmental impacts for it which need to be considered. This T is quite a normal arrangement anyway. So we're obviously talking about a beam that would be going like so. Okay. And what they're saying is that there's going to be you want to keep this plank, the horizontal plank and the vertical plank, you want to keep them, you want to stop them from separating. So to stop them from separating, you could be putting in a nail, so you can see the nail going down there. So there will be a nail there, and if I can draw that, you can't obviously put a nail at every point, so there will be another nail top there, and then that would be going down into the plank, I suppose, and there would be another one down there. So we'll talk about the nail in a second, but you can see there's a spacing between the nails. So you can see there's a spacing, and we'll call that spacing S. Okay, so we'll call that spacing S. So there's again a spacing in the longitudinal direction between each of the nails, and we will say that the nail is spaced at a distance S from each other. So if you looked at maybe we could draw something like that, which would just show that, and so there would be a nail here, for example, and then there will be another nail here going down into it, and then there will be another nail down there, and then the spacing between the nails would be this distance S. Okay, S obviously stands for spacing. So consider the timber beam analysed in example 2, but instead of gluing the two sections, they're now nailed together as shown in this figure here. Each nail can safely transfer a shear force of 1.4 kilonewtons. So what does that mean? So within this system here, we're saying that if all of that was pushed to one side, so if the bottom block was pulled in that direction there, and then this top bit there was pulled in that direction, and then so you could count the number of nails with the spacing. So okay, so 1, 2, 3, 4, 5, 6, 7 nails. And then if you said you did an experiment and you pulled these two apart, so that one is in shear in that direction, and then this one here is in the opposite direction there, you could say that if after you've pulled it over, you've pulled it over so each nail breaks, or each nail is sheared along that shear plane. So I've drawn the nails all to one side. Okay. Alright, so we draw that there, and then that one is obviously come in, and that one is now coming out, and this one here is coming in here because it's moved to the right, and this one's moved to the left. So we've done an experiment and on our beam here, and we've pulled it, and then all of the nails shear. And then if we found out that 1.4 multiplied by 7, because we've got 7 nails, so the failure would be 9.8 kilonewtons. 9.8 kilonewtons. So you'll take the 9.8, you divide that by 1, 2, 3, 4, 5, 6, 7 nails, and then you would say each nail can safely transfer a shear force of 1.4 kilonewtons. And obviously this is in the longitudinal direction, okay, or along the length of the beam. So that's what that means. And you can see these nails that they would just shear off. So if the maximum shear force, again from the shear force diagram, is 10 kilonewtons, then what nail spacing in the direction of the beam length is needed? So the question is basically asking you, the question is basically asking you what spacing is needed between the nail. So back in example 2, we were talking about a shear stress, or a shear stress of the adhesive as it performs in a shear strength test, or the strength of the glue. So what we're talking about now is not the shear stress of a bit of adhesive. We're actually talking about a force, and that can be expressed in terms of what we call the shear flow. So if you remember, the equation the equation for the stress, so we've got shear stress is equal to, I'll just call it the shear force, which you could see as V, multiplied by S dash as a function of Y, and divide that by I, and remember that was multiplied by B, B as a function of Y, and again S dash as a function of Y, and then tau is a function of Y. So that's all okay when we're talking about in terms of stresses, but it would be nice if we could, for example, get rid of that By, because the By doesn't really help us much. So in this case here, we can see all of the force is being transferred by the nail. So we introduce this thing here called shear flow, and the shear flow, so shear flow is exactly the same as that expression there, but it's called Q, and it's equal to the shear force, which is going to be 10, and it's going to be multiplied by, again, your S dash Y from the equation there, and it's just going to be divided by I. So we've managed to get rid of B because we're no longer interested in a stress. We're interested in the shear force that's carried by the nail. So in example 2, we were interested in the strength of the glue. Now we've replaced the glue with a nail, and we're interested in the spacing. Okay, so I hope that you can see that shear stress can be related to shear flow, and if you took shear flow and you divided it by the breadth, then you're back to the stress, to the shear stress. So you could have done the calculation for example 3 based on the shear flow and divided by the breadth B, and you suddenly got the shear stress in the adhesive. So I hope that's not difficult to understand. So now for this one here, so as before, we've calculated that distance to the centroid, which worked out to be probably 162.5 millimeters. We've probably worked out the IX, the second moment of inertia, about the neutral axis or the x-axis, and that probably worked out to be 113.5 times 10 to the 6 millimeters to the fourth. What we're worried here now is what is that shear flow being at the web, the web, so that one is the web, at the web flange interface. So for that, we would take out the flange as we've described before. So that might be the easiest thing. Okay, so we've taken out the flange. Remember, we could take out the web, but if you take out the web, then that area is above the neutral axis and that area is below the neutral axis. So you have to treat these two as separate areas and subtract one from the other. Whereas it's far easier just to consider that area there of the flange, because it's all above the neutral axis. Going back to these two equations. Okay. So we would want to know what S-y is. So S-y is nothing more than 200 times 50 multiplied by the distance from the centroid of that shape to the neutral axis. So nothing more than the area of that shape multiplied by that distance. Okay. So we've done it before anyway, and so the S dash, yeah, I just call it S dash, maybe S dash flange might be. The S dash of the flange is going to be equal to 625,000 millimeters cubed. Okay, so we've got our S dash both for the stress, so that this equation is to work out the stress at any point, and this equation is to work out the flow. So we want to know the flow at that point there, because that's where the nail would be sheared, because you've got two planes, of course, which are moving in opposite directions. So we've now look at this equation here. We've got the shear flow is equal to the shear force. So we know the shear force because we've been told it in the question that it's 10 kilonewtons. And then we know the S-y, which we've worked out to be 625,000 millimeters cubed. And then we know I of the compound section, which we've calculated before. And then from there you could work that all out and you will get 0.055 kilonewtons per millimeter. So you can see the units of the shear flow. The units of this one here, if you calculate it, would be millimeters squared, and here the shear flow is the force just per millimeter. So what's the required spacing? So the required spacing is, we know that each nail from a test, so each nail can take 1.4 kilonewtons. So therefore, what is the spacing? So then I would say spacing is going to be equal to the shear force that each nail can take which would be 1.4 kilonewtons. And then if you divide that by the shear flow, which has come out as 0.055 kilonewtons per millimeter. So note that these two would go, then the millimeters would go to the top, and then you've got 25.5 millimeters. Okay. So this is, so you can see that we don't even need to bother about the shear stress. Instead of thinking in terms of a stress, we think of a flow going through there per millimeter, the millimeter being in that direction there. Just divide the 1.4, which is the strength of each nail, by the shear flow, which is per millimeter, and you would get the required spacing. You would get the required spacing of each nail. So if for example that T-section had been a simply supported beam, like there, with 20 coming down here, so we'll have the shear force diagram looking something like that, and within the length you would expect there to be a spacing, a nail spacing of 25.5 millimeters. So the nails would have to be applied at the distance of 25.5 millimeters from each other. So hopefully that shows the concept of shear flow, but shear flow is of course very, very similar to the shear stress, and it's just getting rid of this factor, it's just getting rid of this B. So, the solution is written out here in the Dropbox, which you can see there, and the video that I did last year is also in the Dropbox as another explanation. Okay, so let's move on to example number 4. So in example number 4, a 600 by 300 welded box beam is to be fabricated by welding 20mm thick flange plates to 12mm thick wet plates using fillet welds, as shown in this figure here. The beam will be subject to a maximum shear force of 1750. Determine the maximum shear stress in the web. So the first thing here is work out the shear stress in the web, and then the second bit is determine the demand on each weld in units of kilonewtons per millimeter length of weld, and choose the appropriate weld size from table 1. So the first bit of the question is work out the shear stress halfway at mid height. So we would of course be able to say by inspection that the neutral axis would be going through mid height anyway. So that's where our y-axis would start, and then that's obviously the x-axis there. So to work out the shear stress there, we would have our equation, tau is equal to the shear force, 1750, and that's going to be multiplied by S dash y divided by I, and that's going to be multiplied by b, which is the breadth, which is the b. Okay, So that's the equation that we would be needing to solve to work out what the shear stress is at here. Now, so one confusion there's probably no confusion to work out that. There's probably no confusion to work out S-Y, and there's probably no confusion to work out I. You know, you've been given all the dimensions, and using parallel axis theorem, you should be able to work out I, and you should be able to work out the area of these three parts here, find the centroid, and work out what the S-Y is. So all of that's given in the solution anyway. So I'd just like to concentrate on what this BY should be. Now, so I think you've got two options. Your BY could be 12, or the BY could be 12 plus 12, which is 24. So if you just pretended that you took this web here and you moved it there, and if you took this web here and if you moved it there, so we've moved the webs until they're at the center and they're touching each other. You just pretended you moved across. I hope you can see that no part of this equation would change. So the shear force is still the same. The S dash, that wouldn't change. The I wouldn't change. And you can immediately see that the breadth here at the center is going to be 24. So if there's any confusion with the use of this equation here, I think it should be obvious that when you work out the shear stress, it should be 24. Okay. So I'll take that out with the rubber. But if you just looked at the equation long and hard enough, you could probably see that nothing should change if the webs are moved closer to each other until they're almost touching, and then it should be very obvious that you should be using 24. So the next part of the question then is about these welds. So this is about the stress, and then this is about the welds. So the weld, the strength of the weld is given by kilonewtons per millimeter. So that means it's very similar to what we talked about here for the nails. So we've got a weld. Now Gary's probably talked to you about welds, but you can have different weld sizes. So that could be 5 millimeters and that could be 5 millimeters. And then you've got a choice. Do you weld it with a 5 millimeter weld, or do you weld it with a 12 millimeter weld, for example? So obviously, if you increase the weld size, you're going to be increasing a lot of cost, but the strength of the weld in kilonewtons per millimeter, millimeters being in that direction there, obviously increases by quite a lot. So this is clearly a shear flow issue. So we're interested in the flow that's carried by each weld. Okay. So let's have a look at the solution first. So as before, I've got a few pages of YouTube Live Scribe, which talk you through the problem. But if you don't want to go through my Live Scribe, then there's a typed solution in the Dropbox. So the first thing to do is to work out the maximum stress in the weld, and you can see that they've used the 24 because you can see the 12 and the 12 there. Sorry, to work out the section properties, and then you can see how everything's been calculated here. Divide by I that you just calculated, and then the B in this case here is the 12 plus the 12 for the reasons that I've just explained. So note that B in the formula has been replaced by the sum of the widths, since this is the total width of the material available to carry the shear stress at the slice location. This assumption is made that the stress in each web would be the same, justified by symmetry. If the webs were of different thickness, or if there was some other symmetry, then we could only calculate the total shear flow at the slice. Determine how it was divided between the webs would need some further consideration. So because they're both the same, you can add them together for the reasons that I've just described. Now the force carried by each weld, so for this we would need to determine the shear flow at the junction of the weld and the top flange. So we take our slice here, just being on the top here, so we can take our slice there. Now let me just show where the slice is. So that's the neutral axis of the section, and we are taking the slice through here. Okay, so that means that when we work out our S dash, so we've taken the slice here, so we forget about those bits there. So to work out the S dash, it's 300 multiplied by 20 because that's the area, and then the distance from the neutral axis to the centroid of this shaded area is going to be 300 minus 10, which is 290. So come up to there, down there, that's going to be your 290. So I hope that's clear. And then I is of course the I of the whole section. So that's the expression for Q, which is the shear flow, or the shear that flows into the top section there. And we would say, since there are two identical welds, 1 and 2, cut by the slice, we apportion half the shear flow to each, giving for each weld a demand of 1.12 kilonewton per millimeter. So if we now go over the next page, this one just gives some pragmatic reasoning that says that this one, we calculate 1.12, and yes, 1.12 is bigger than 8, but it's just so close. 1.11 is very, very close to 1.12. So pragmatically, we could say just use 8 because it's close enough, and there's no need to go to the extra expense of going up to a weld size of 10. So that's the justification. So the answer is choose this world size. So if you're not quite okay with that reasoning for why we divide the shear flow by 2, then another way to handle it would be, you could, instead of taking the top slice from there, you could say, I'm just going to be handling that area there. And if you handle just that area there, work out your your A, so the A would be half, the Y would be the same, that one would be the same. You would get the shear flow going through a single weld. Right. So hopefully that's clear enough to deal with this problem here. But if it's not, then you can jump into the LiveScribe. You can jump into the LiveScribe solutions that I've provided, where more detail is given. So in the Dropbox under here, I provided John's solution, the type solution here. So that's been provided, and you've got my YouTube solution. And if you wanted to, you could have a look as to how I explained it in the video last year. Where so last year, of course, I had a printer, I had more stuff, I had a more stable camera, so I may have been able to explain things a bit clearer. All right. So, but yeah, hopefully that's enough. So we're coming on to the topic of thin walled sections. So shear in thin walled open sections. So we'll cover that. Next time in the last lecture on shear. But if you wanted to play with this before, so here's a sheet of paper, and if we fold it, then we get a thin walled channel section, which you can see here. And if you look around here, you can see the direction of the, so that's the vertical shear, which you can see down there, and you can see that shear there. So that's actually the shear flow, and that's actually the shear flow on the other side. So if you looked at it, you would be able to see shear flow going in that direction and shear flow at the bottom going in the opposite direction. So just have a look at those arrows, and we can see horizontal shear in the flange there, vertical shear in the web, horizontal shear in the flange, and when you draw the cross section, you can see the shear flowing round. Okay, so you can see the shear flowing around, which means that a section like this actually wants to twist unless the load is applied at the shear center, and we'll calculate the position of the shear center next time round. And feel free to have a look at some of the other resources here. These are basically student explanations for common problems. Okay.